Oliver today, who will tell us about topological invariant of helicity.
Thanks a lot for giving me the opportunity to speak here. I will talk about helicity and some C0 properties of it, and this is all going to be joint work with Sobhan Seyfaddini. Just let me know if you have any questions or can't hear me well or anything like that. So I should start by explaining what helicity is. As our setting is going to be a closed three-manifold Y that's equipped with a volume form mu. And just for simplicity of the talk, I want Y to be the three-sphere, but this is not a necessary assumption. One can drop this quite easily. On this three-manifold, I want to look at a volume-preserving vector field X. And then helicity is a real-valued invariant of such volume-preserving vector fields. And the most economic definition goes as follows. So first one forms the product of or the contraction of the vector field in the volume form. This gives a two-form omega, and because X is volume-preserving, this is a closed two-form. Now, because we are in the three-sphere, so that's where the simplification comes in, this closed two-form actually is exact, so one can choose a primitive one-form alpha, that is alpha here. And then helicity is defined by this integral here, where one takes the integral of the three-form alpha wedge d alpha over the three-manifold Y. And then there's a short argument that shows that this actually is independent of the choice of this one-form alpha. So this expression here, this differential form here, is familiar from contact geometry, so that would be the contact volume of a contact form. But here we are more general than that. We really take any volume-preserving vector field, and this might not be a contact type situation. So the fundamental property of helicity that's very important for this talk is its invariance under volume-preserving diffeomorphisms. If F is a volume-preserving diffeomorphism for a three-manifold, then the helicity of the pullback of the vector field under this diffeomorphism is the same as the original helicity. So it's quite straightforward to prove this with our definition of helicity here. One simply has to notice that if one replaces X by the pullback, one can also just replace the one form alpha by the pullback because the diffeomorphism preserved the volume form. And then it's a relatively short computation to check that helicity is invariant. So now where does this construction come from? The origin is in hydrodynamics and in, this should not be in brackets, just in hydrodynamics. And it was introduced in this context as a conserved quantity. An example is the motion of an ideal fluid. So that's a fluid that's incompressible and moves without friction. That's described by the Euler equations. So in such a fluid, one has a velocity vector field. That's a time-dependent vector field. And at each time, it tells you how the fluid particles move at the different locations in space. But it's a second vector field. It's called the vorticity vector field. That's also important in a fluid. It's the curl of the velocity field. And that one tells you how the fluid element turns at a prescribed location and time. There's a very old theorem that goes back to Helmholtz and Kelvin, and that says that this vorticity vector field evolves in a very special way. So what happens is that the vorticity vector field at time t is simply the push forward of the vector field at time 0 under this map phi here. And this map phi is the flow that's induced by the time-dependent velocity field. So this phi tells one how the fluid particles move around in space. And the consequence of this is that the helicity is a conserved quantity of the fluid. And this follows from the invariance, right? So because it's an incompressible fluid, our phi is the volume-preserving diffeomorphism. and then the helicity was invariant in the pull back or push forward under such things. So it's constant in time. That's the origin. Yeah, so now Arnold gave an alternative description of helicity that illuminates a little bit better what this quantity is supposed to measure. And this works as follows. So this description is based on the flow generated by the vector field, and in particular on the linking of flow lines. So what one does is that one picks an initial point P and an initial point Q in the three-manifold. And then we pick some, so our goal is to measure the linking of the two flow lines starting at these 2 points. And one does this as follows. One picks two large but finite times S and D. And then one looks at the corresponding finite flow line segments. So the P flows for some time and ends up at phi S of P. And the Q flows for some time and then ends up at the phi T of Q. So when one gets these two potentially very entangled flow line segments, to get a linking number, we want a link, so two loops. And to get loops, what one does is one simply closes up the flow line segments by some reasonable choice of short path. So for example, one pick an auxiliary metric and make a choice of shortest geodesic segment. Then one gets a linking number for every point P and Q and for times S and T. And the next step is to let the time go to infinity and take an average. So there's an ergodic theorem that tells us that if one does this, one gets a well-defined linking number, asymptotic linking number for almost every pair of points P and Q. And moreover, the result is an integrable function. So one can integrate it over the product of the manifold with itself. And then Arnold proved that this exactly recovers the helicity as defined previously in terms of differential forms. One also should mention the work of Vogel here. So Arnold was not 100% precise about everything, and then Vogel later made this proof fully rigorous. Okay, so now Arnold asked the following question. The first question he asked is whether helicity is also invariant under conjugation by volume-preserving homeomorphisms. So here's what this means precisely. If we have two smooth volume-preserving vector fields, an x1 and an x2, they both generate flows. And if we assume that there exists some volume-preserving homeomorphism, also orientation-preserving, that's this plus here, such that the two flows are conjugated in this sense for all times t. The question is whether these two vector fields then share the same helicity. So if F is a diffeomorphism or any sort of regularity, then this is this previous invariance that I explained, and Arnold wanted to know does this extend and just for homeomorphisms with no extra regularity. And then the second question is an extension question. So one wants to know whether one can define helicity for C0 volume-preserving flows. And what I mean by this here is a continuous group homomorphism from R to the volume-preserving homeomorphism group. Given such a phi, is there any sense in which, any way in which we can define an extended helicity? Yeah, the second question is supposed to be the harder and more general one. So the reason is one wants this extension to be reasonable in some form. So in particular, it should be invariant under homeomorphisms. If it's defined for C0 flows, it should be invariant under those. So then it would imply ideally the invariance part. There are some motivations for this question. The first one is just from the point of view of dynamics. So we have helicity, it's a priori a smooth invariant of smooth flows. So one can ask, is it actually a C0 topological invariant? That's a natural question. There also is motivation coming from fluid dynamics. So recall that in this context, helicity was this conserved quantity, and the helicity of this vorticity vector field that's conserved. Yeah, I mean, this is a bit of a vague motivation, but you could imagine a smooth fluid that evolves and maybe at some point runs into singularities. And then you could wonder, does helicity conservation maybe make sense beyond this point? So in this context, it could be interesting to understand homeomorphisms. Another motivation just comes from C0 symplectic geometry. So this is an interesting field in symplectic geometry. So, well, one likes to find applications of that. Okay, now why? So, what is interesting or hard about the question? Right, so we can first examine the original definition in terms of differential forms. Right, so here one forms this 2 form omega, big the primitive 1 from alpha, and takes this integral. And yeah, if one wants to prove or answer the question based on this definition, one runs into some immediate problems. So for the invariance question, in the smooth setting, there was this pullback of alpha under a diffeomorphism F involved. But if F is just a homeomorphism, one doesn't know how to define this. And then for the extension question, if our C0 flow just was this continuous group homomorphism into the volume-serving homeomorphism group, then there might not even be a vector field. So then, yeah, one doesn't quite know what to write here. Now, the second description that Arnold gave, here one can be maybe more hopeful at first, and this maybe also was the motivation of Arnold for asking the question in the first place. So if one has some link with a linking number, and the second link that's homeomorphic to it, that of course has the same linking number. So the linking number of links is preserved in the homeomorphisms. But in our setting here of this asymptotic linking number, there's an important subtlety that lies in these short geodesic arcs that one used to close up the finite flow line segments. So here I zoomed in the earlier picture at this geodesic arc. And the problem is that some conjugating homeomorphism, it will conjugate flow line segments. So that's fine. So this green flow line segment goes to a nice green flow line segment, and the blue one to a blue one. That's all good. But this geodesic arc here, it's not in general going to a geodesic arc. It's just going to some potentially very rough and windy C0 arc. So I tried to sketch one here. And yeah, so our conjugating homeomorphism, just a homeomorphism, there could be some sort of infinite twisting going on. So in principle, this geodesic arc on the left side could be mapped to something that twists arbitrarily much somewhere. And then there's just no good way anymore to control how the linking number changes if we go from the left side before the conjugation to the right side after conjugation. So that's one subtlety here. And then there's a related subtlety for the extension question. So one can find the C0 flow, one can define one where there's a lot of twisting near some flow line. And in particular, one can arrange it such that the asymptotic linking number is no longer an integrable function, as then one doesn't know how to make sense of this formula. Right, so it's yeah, not immediately clear how to approach this question. Right, so now here is the result I want to talk about today. So I repeated here Arnold's question, and then what we're able to show is that the answer to the invariance question is yes, if we restrict to volume-serving smooth vector fields that have no zeros. That's a nice big class of vector fields, and for those one has the invariance. And then we deduce this from an extension, and our extension is to C0 flows that have, first of all, no rest points. So there's no rest point assumption that corresponds to the no zeros in the smooth vector field. That's the C0 version of that. And then we need a second assumption, and this one demands that there's no individual periodic orbit in the flow that has positive measure. So this is trying to rule out some rather pathological flows. It can happen for such C0 flows that one has one single periodic orbit, and its three-dimensional measure is 99% of the total measure of the three-manifold. And this kind of thing we want to rule out. It's not quite clear whether there's much reasonable things to be said about that. Right. And then, yeah, so the relevance of this no zeros, so no rest point assumption is that we connect the whole story to foliations. And if one has a vector field with no zeros or a C0 flow with no rest points, then the flow lines form a one-dimensional foliation. And that's useful for us. Right, so this is the main result. Now I should also mention some previous works. So a particularly nice one is this work of Gambaudo and Gies. And there they answer the invariance question for disk map suspensions. So one would take a two-dimensional disk and a compactly supported error-preserving diffeomorphism. Then one can form a mapping torus, and then one can complete or compactify that to a volume preserving flow on a closed manifold. And then if one has two smooth vector fields that come from this construction that are also conjugated by a homeomorphism, then Gambaudo-Gies showed that one has the invariance. So the two vector fields have the same helicity. There also is work of Müller and Spath, and this already connects the question a little bit to C0 symplectic geometry. The precise result is a little bit technical to state, so they have an extension to what they call continuous strictly contact isotopies. So for the expert, this would, it's very much related to the fact that homeomorphism isotopy has a unique C0 Hamiltonian generating it. So this work is connected to these kind of ideas. And then also there's a very recent work that appeared in the archive actually this week. So I need a bit more time to digest it. It's by Giri, Kwon, and Novak. So these are people working in fluid dynamics. And what they did is they defined an extension for helicity, but not for C0 flows, but for some very low regularity class of vector fields. And then what their work also does is they produce weak solutions to the Euler equations, where then their extension of helicity actually is not preserved under the evolution. Now, this whole work somehow goes a little bit in a different direction from ours. Right? In our work, well, we have C0 flow, but there might not be any vector fields in the background. And what they have is low regularity vector fields, but they might not have any good sense of flow they generate. But yeah, it would be interesting to compare these two works more in the future. Okay, now, yeah, so now I want to say, go a little bit into how we prove this theorem on invariance and extension. Yeah, so the first step, and I already briefly mentioned that, is that we want to connect the theory of foliations. And so here's what we do in the smooth setting. So in the smooth setting, we have our three-manifold, the volume form, and a smooth vector field, volume preserving with no zeros. And this structure induces, first of all, a one-dimensional smooth foliation. So the leaves of that are just flow lines of the flow generated by the vector field X. There also is a transverse measure present. So there's this two-form omega that's obtained by contracting the vector field into volume form. Now this two-form omega, its kernel exactly is tangent to the foliation, and one has this smooth area form in the transverse direction, and one can interpret this as a transverse measure. So the transverse measure is a structure that induces a measure on every transversal surface to the foliation. And there's a version of the Booth theorem here. So our structure is locally diffeomorphic to a standard chart. So the standard chart is interval across the disk. So here the foliation would be tangent to this interval vector. And the transverse measure comes from the standard area form on the disk. Okay, and so the idea is we want to so if we have such a flow, it induces this structure, and we'll then mostly be interested in this smooth measured foliation. My notation for these structures will be little omega, the same as this two form. So this means the whole thing, this one-dimensional foliation plus transverse measure subject to the property of locally being diffeomorphic to the standard piece. And this sometimes is also called a Hamiltonian structure in literature. It's just a closed, smooth, maximally non-degenerate two form on a three-manifold. Okay, now in the C0 setting, one starts with the three-manifold Y, a volume form, and the rest point 3 volume-preserving flow phi. And this also gives a one-dimensional foliation by the flow lines of phi, but now it's just a C0 foliation. There still is a transverse measure. One no longer can make sense of this two form, but one can get a transverse measure defined as follows. So one just picks a transverse piece of surface to the flow, and then one can flow for some time epsilon and measure the three-dimensional volume that's swept out by that. And if one divides that by epsilon, this induces a two-dimensional measure on this transverse surface piece. So one still has this in the C0 world. So this whole structure still will be locally homeomorphic to a standard chart. And I didn't forget to write it here, but here is where the assumption on no periodic orbits have positive measure comes in. So if there was a periodic orbit of positive measure, then this transverse measure would have an atom. So there would be a transverse surface, and then the intersection point with the periodic orbit of positive measure would be a point of positive measure on the transverse surface. But by our assumption, there's no atoms in this transverse measure. And then there's a theorem of Oxtoby and Ulam that tells one that one is locally homeomorphic to the standard chart. Right, and my notation for these C0 measured foliations will be a capital omega as opposed to a lowercase omega. And in our paper, we called these things also C0 Hamiltonian structures, in analogy to the Hamiltonian structure in the smooth case. Right, and yeah, so it is possible now to view helicity as an invariant of just a Hamiltonian structure, omega, instead of this whole tuple of volume form and volumes in vector field. Right? So if you recall the very first definition of helicity, one simply had to pick a primitive one form alpha of this omega, and the helicity was defined in terms of alpha. So helicity only depends actually on this structure. So one can just remember this Hamiltonian structure and forget this whole tuple of volume form and vector field, and helicity will be an invariant of that. And then if one does that, one can reformulate the questions. The invariance question becomes, is helicity of the Hamiltonian structure invariant under now just orientation preserving homomorphisms? So here one actually threw out the volume form. Now it's just any homomorphism that's just orientation preserving that conjugates these two Hamiltonian structures, where this is understood as measured foliations. So one can't pull back the two form, but as measured foliations, this whole thing makes sense. And then, yeah, we want to know whether these two Hamiltonian structures have the same helicity. And extension, well, we want to define helicity for a C0 Hamiltonian structure. Okay, and so here is an important operation in our whole story that we call plug insertion. So there's an operation that modifies locally our measured foliations. So it works both in the smooth and in the C0 setting. So one starts with a trivial foliation chart. This would be just a cylinder of the form interval cross surface with some area form on the surface and some embedding of the structure into our Hamiltonian structure. Our surface will always be open connected. And in addition, we take an Hamiltonian isotopy compactly supported on our surface sigma. And giving this information, one can now modify the measured foliation by inserting this Hamiltonian isotopy into the trivial foliation chart. So when once the new leaves that at first were just horizontal in the trivial chart, one wants them to trace out this Hamiltonian isotopy. So an individual leaf in here would be of this form, a set of 4 points t comma phi t of p, and t ranges over the interval. Yeah, so one can carry this out in the smooth settings. One takes a smooth Hamiltonian structure, a smooth chart, and a smooth isotopy, and one gets back a smooth Hamiltonian structure. And I will use this kind of notation here. So that's the original Hamiltonian structure, and then P stands for this whole data here of the trivial chart and the isotopy. And then one can also carry it out in the C0 world, where one has a C0 Hamiltonian structure, a C0 chart, and then an isotopy in the Hamiltonian homeomorphism group of the surface, where this group is the C0 closure of the diffeomorphism group inside the homeomorphism group. And then the new C0 Hamiltonian structure would be denoted like this. Okay, and now here comes a crucial observation that already is present in the work of Gambado and Cheese that I mentioned earlier. So there's a very simple formula in the smooth setting that tells one how helicity changes if one performs this plug insertion operation. So if we start with a smooth Hamiltonian structure and we put in a smooth Hamiltonian isotopy locally in some chart, it turns out that the helicity exactly changes by the Calabi invariant of the time one map of the Hamiltonian isotopy. So Calabi is this group homomorphism from the Hamiltonian compact supported Hamiltonian diffeomorphism group of our open surface sigma to the real numbers. One way of defining it is in terms of this integral here over one choice h of compactly supported Hamiltonian generating our diffeomorphism phi. So one has this group homomorphism, and yeah, one gets this very nice relationship between helicity and the Calabi homomorphism. So in some sense, one can think of helicity as generalizing the Calabi homomorphism. Yeah, there's this important result of Banyaga that essentially is saying that there's not that many more interesting group homomorphisms out of this Hamiltonian diffeomorphism group. Banyaga proved that the kernel of the Calabi homomorphism is equal to the commutator group of the Hamiltonian diffeomorphism group, and it also is a simple and perfect group. So there's, like any homomorphism out of this group has a kernel which is a normal subgroup, but then there is not that many normal subgroups, basically only this commutator subgroup, and this gives rise to this Calabi homomorphism. One can now essentially reformulate the observation up here on the helicity change under plug insertion as follows. One can observe that if we put some plug P into a smooth Hamiltonian structure, then the amount by which helicity changes, it did not depend on which Hamiltonian structure one puts the plug into. It also doesn't depend on the embedding of the trivial chart, where one puts the plug into. It only depends on the residue class of the time one map of the isotopy that is part of the plug data inside the abelianization of the Hamiltonian diffeomorphism group. So this is the quotient of the group by the commutator subgroup. And if I put some plug into some smooth Hamiltonian structure, the amount which helicity changes, it only needs to know this residue class and nothing else. And so in some sense, this whole property as it's formulated, there's a clear guess as to how one should generalize this to the C0 world. One would want to say that if one puts in some C0 plug, then the helicity change only depends on the residue class now in the abelianization of the Hamiltonian homeomorphism group. And so in some sense, our work in the C0 setting is saying that if one demands such a property to hold in the C0 world, there's a unique way of extending helicity. This will be the spirit of the next result I'm leading up to. Now, before I can formulate it, we need a little bit more of preparation. So now let's look at two open connected surfaces. There's sigma prime and a sigma, and then some error-preserving embedding of sigma prime into sigma. If one has such an embedding, one can look at this diagram here. So we have on the top the homomorphism from the abelianization of the Hamiltonian diffeomorphism group to the real numbers induced by the Calabi homomorphism. And this is a group isomorphism exactly by Banyagas theorem that tells one that the kernel of Calabi exactly was the commutator subgroup, which is the thing that we quotiented out here. One has the same kind of isomorphism for the other surface, sigma prime. And then there's a map induced by push forward of compactly supported diffeomorphisms under this embedding iota. And this whole diagram is commutative. One can see this just from the definition of Calabi. One can take a Hamiltonian here and then push it forward, and then the integral of the push forward is the integral of the original Hamiltonian. So one gets this homomorphism here. And because the diagram commutes and because both homomorphisms induced by Calabi are isomorphisms, this push forward by iota actually is a group isomorphism. And also it is independent of the choice of embedding iota. So it says for any two open connected surfaces, this abelianizations are isomorphic. So it doesn't matter whether the surface is a disk or has some genus, they're all isomorphic. And moreover, they are naturally isomorphic in a way compatible with maps induced by inclusions. So that's all in the smooth setting. And it follows from Banyaga's result. So the proof of this is somewhat involved. So Banyaga's theorem is hard to prove. So in our work, it was useful to have a C0 version of this. So what we proved is that if one looks at group homomorphisms induced by C0 error-preserving embeddings, they also induce an isomorphism of abelianizations of Hamiltonian homeomorphism groups. And again, one has independence of iota. So this means that if one has any surface open and connected, it takes the Hamiltonian homeomorphism group and then takes stabilization. The result is naturally isomorphic to the group associated to any surface. So one can, for example, pick the standard disk, the standard area form. Like all of these groups are naturally isomorphic to this one here. So one can give it a name. We called it curly R in our work. Now, there already is some interesting consequence here. So what this is ridiculous saying is that, and I will come back to this later, but for those for the experts, it means that once one knows the simplicity conjecture for the disk, one can, using this proposition, get it for any other open connected surface. This already was known, so there's yeah, I will say more about this later in a bit. So this is known, but yeah, one can get these results alternatively through this proposition once one has the case of the disk. Okay, now here is our theorem. I introduced some notation. So in this whole diagram, in the bottom row, we simply have the smooth Calabi homomorphism from the Hamiltonian diffeomorphism group. And now we can think of it as well, first projecting onto the abelianization, and then we have this natural isomorphisms between the abelianization and the real numbers. So we can identify those two, and we can think of the smooth Calabi homomorphism in this way. And then in the top row, I mean, we still have a natural projection from the Hamiltonian homeomorphism group onto the abelianization of the Hamiltonian homeomorphism group. And well, then because all of these were naturally isomorphic, we called them curly R. And then this whole topological projection, I want to give it the name Cal bar. So in some sense, we think of it as an extension, although tautological, of the smooth Calabi homomorphism. So in particular, one has this natural homomorphism from the real numbers to the curly R that's induced by this homomorphism here from the abelianization of the smooth diffeomorphism group to the abelianization of the Hamiltonian homeomorphism group. Okay, and now here's the theorem that we proved that really underlies this earlier main result I stated. So we proved that there's a unique way of assigning an extended helicity, taking values in this curly R in the abelianization of the Hamiltonian homeomorphism group, to assign such a thing to every C0 Hamiltonian structure, capital omega, subject to three extremely natural properties. The first property is saying that this extended helicity should extend the smooth helicity. Right? So if one has a smooth Hamiltonian structure, one can take its smooth helicity, which is a real number. And well, one can also think of the smooth Hamiltonian structure as a C0 Hamiltonian structure, and then one would get this extended helicity that the theorem claims exists. That takes value in the curly R. And we demand that if we map the smooth helicity from the real numbers over to the curly R, we exactly should land at the extended helicity. So this is natural to demand. Well, any extension really should have the property of extending. Now the second property is equally natural. Here we demand that our extended helicity, extension is into C0 Hamiltonian structures, should be invariant under orientation preserving homeomorphisms. Well, of course, we want to have this property. If it's defined for C0 structures, it should be invariant under homeomorphisms. So there's no negotiation about that. And then what we proved is that if one just adds one additional property, then this uniquely specifies what the helicity extension has to be. And this property is this kind of C0 version of the observation of Gambardou and Schiess on the relationship between helicity and Calabi. So we want to demand that if one starts with any C0 Hamiltonian structure and puts in any C0 block, so we insert some isotopy of Hamiltonian homeomorphisms, then the extended helicity should exactly change by this extended Calabi invariant of the time one map of the isotopy. And recall this was simply the residue class of the time one map in this abelianization. Right. And so we say that there exists an extension with these properties, and there's exactly one such extension. There's more. So the theorem continues. So one could complain maybe that, well, this extension here, it takes values in this strange group, curly R, the abelianization of the Hamiltonian homeomorphism group, and not in the real numbers. So how about real valued extensions? And the situation here is the following. So if we assume that we have some real valued extension of helicity to C0 Hamiltonian structures, and assume that this extension satisfies of the analogs of properties 1 and 2 above. So property 1, if it's a real valued extension of helicity, well, yeah, it's simply just saying that the Hell bar of a smooth Hamiltonian structure is exactly the same as the extended one. And then the version of property 2, yeah, this extension should be invariant in the homeomorphisms. Okay, let's assume that our extension also has the property 3 prime. It's a bit different from this one here. We assume that the helicity change under plug insertion does not depend on where one puts the plug. It only depends on the time one map of the isotopy one inserts. So this was this property that I observed above that holds in the smooth case. And if one assumes one has an extension that has the C0 analog of this property, then this extension actually is of the form L bar. So this is this extension up here, taking values in the curly R, composed with homomorphism P from the curly R to the R. So this is some sort of projection. So we are saying that if one has a real valued extension that has these very natural properties, then it must be of this form. And actually, more is true. So if one defines the extension this way for some choice of homomorphism from the curly R to the R, then it also will have these three natural properties. Right. So in some sense, if one insists on helicity, a real valued helicity extension to be well behaved with respect to this insertion of plugs, then real valued extensions of helicity are in one-to-one correspondence with such homomorphisms P from the curly R to the R. Yeah, so in this sense, our helicity extension, the first part of the theorem, is universal. Like any other one will just derive from that. Okay, so now, right, so we have this theorem, but for this theorem to really be useful, we actually would want to know a little bit more about this homomorphism from the real numbers to the curly R. Might recall this was this homomorphism that's induced by, that is the map that's induced by the inclusion of the Hamiltonian diffeomorphism group into the Hamiltonian homeomorphism group. So one wants to know more about this map. In particular, a priori, and this actually was a long-standing open question of the simplicity conjecture, it's not even clear whether this curly R is a trivial group or not. So if the R, for example, is a trivial group, then, well, our extension was a bit boring. So then more or less we would have proved that it is not possible to extend helicity in a reasonable way subject to good behavior with respect to plugs. So we want to know that the R is non-trivial. And also we would maybe want to know that this homomorphism is injective, for example. Right, so now what is known about this homomorphism? And there have been a lot of very interesting works on this in C0 symplectic geometry in the recent years. So what do we know? First of all, there's the work of Christopher Gardner, Humilier, and Seyfaddini that resolved the simplicity conjecture, and this is equivalent to so what they proved is that this group curly R is not the trivial group. So that's good. So our extension is not trivial. And then later on, they joined forces with Mack and Smith. And in this later work, there's this set of Floer theoretic spectral invariants called link spectral invariants that plays an important role. And what one gets out of the link spectral invariance is a sequence of quasimorphisms from the Hamiltonian homeomorphism group to the real numbers. So there's one such link spectral invariant for every positive integer d. These are not group homomorphisms, but they are quasimorphisms. So they're homomorphisms up to some bounded error called the defect. And what is also true for these link spectral invariants is that the defect actually converges to zero as the d goes to infinity. So the error in the CT not being a homomorphism gets smaller and smaller as the d increases. And now one can look at this diagram, and this diagram tells us pretty much everything that's known about this group curly R. Right, on the bottom row, we again have the smooth Calabi homomorphism. So there's this canonical projection to the ablonization, and then the natural isomorphism to R. On the top row, we have this projection from the Hamiltonian homeomorphism group to the curly R. So this is what I earlier called overline Cal. This was this extended Calabi homomorphism. And using the link spectral invariance, one can also define a group homomorphism from the Hamiltonian homeomorphism group to this vector space here. So one first looks at the vector space of all sequences of real numbers. And then, of course, one can input a homeomorphism and then output the sequence of link spectral invariants that lands in this space of sequences. Now, because the CDs only were quasimorphisms, this is not a group homomorphism. But because the defects go to zero if one quotients out by zero sequences, so sequences of real numbers converging to zero, then one turns the resulting induced map into a group homomorphism. So one gets this map up here. And then there's the diagonal map that inputs a real number and outputs a constant sequence. And the remarkable fact is that this whole diagram is a commutative diagram. This means if we start with a Hamiltonian diffeomorphism, we take its Calabi invariant, and then we look at the constant sequence where each entry is the Calabi invariant of the diffeomorphism. In this vector space, that's the same thing as first thinking of the diffeomorphism as a homeomorphism, and then looking at the sequence of link spectral invariants. So this is the same thing, and the reason for this being the same thing, this is what is called the Weil law. So it turns out that if one starts with a diffeomorphism, then the sequence of link spectral invariants, it converges to the Calabi invariant of the diffeomorphism, and this exactly is a reformulation of the statement that this whole diagram here is a commutative diagram. Okay, so I claim that everything we know about the curly R essentially follows from this commutative diagram. Now, the first important observation is that the map from the real numbers to the curly R that's induced by including diffeomorphisms into homeomorphisms. This is an injective map, and one can see this from this diagram here, because the diagonal homomorphism that takes a real number and goes to the constant sequence, this is an injective group homomorphism, and the diagram commutes. So if we go diagonally, it's the same thing as going up and then going right. But if this composition up and then right is injective, then the map that goes up must have been an injective one. We can also see that the map from R to curly R is not a surjection, because it is known that the curly R does surject onto this very big vector space of all sequences mod zero sequences. So in some sense, one should think of the curly R as being quite a bit bigger than the real numbers. Yeah, and so this whole fact really is it is a very deep fact. So the only proof we have of this really follows from this whole story with the link spectral invariance. And it also really is what makes this theorem above on the curly R valued universal helicity extension useful. So if one wants to, for example, deduce the invariance of helicity just for smooth Hamiltonian structures, it really uses its injectivity. So what we want is we take two smooth Hamiltonian structures, omega 0 and omega 1, and if we assume that they're related by a orientation preserving homeomorphism F, right, we want to conclude that the ordinary smooth real value helicities are the same. And now we can prove this quite easily, right? So we can take the smooth helicity of omega 0, take the smooth helicity of omega 1. That gives us two real numbers. And we can also think of omega 0 and omega 1. We can view it as a special case of a C0 Hamiltonian structure, and we get two extended helicities, overline hell, that both take values in the curly R. Now, it was one of the properties in the theorem, first one, the extension part, that if one starts with a smooth Hamiltonian structure, thinks of it as a C0 one, and then moves forward the smooth helicity into the curly R by the natural map, then exactly one gets the extended helicity. So the ordinary helicity maps to the extended helicity by the first property in the theorem. And then by the second property in the theorem, because the extended helicity is invariant in the homeomorphisms, the two extended helicities on the right-hand side here, they must be the same, right? Because our two smooth Hamiltonian structures were conjugated by a homeomorphism. And then because the natural map from R to the curly R was injective, one can deduce from the extended helicities on the right being the same that the initial helicities on the left were the same. Okay, so this is how invariance follows. One also can deduce from this diagram that there exist projection maps from the curly R back to the real numbers. Right, and Zurich also explained that such projection maps from the curly R to the R, they are in one-to-one correspondence with real valued helicity extensions. So if one wants to know whether a real value helicity extension exists, then we have to know, does such a projection exist? And from this diagram up here, one can deduce that a projection does indeed exist, because one can choose a projection of this vector space of sequences of real numbers, modulo 0 sequences, to the subspace. That's the image of the inclusion of R here. One can choose such a projection that gives a projection from curly R to R, and this gives a real value helicity extension. Now, it's important to point out that there isn't really a natural choice of projection from this space of sequences to the real numbers. Really, any such choice really uses the axiom of choice. So it's not going to be an extremely natural object. And moreover, there's many possible extensions if one accepts the axiom of choice. Right. So in some sense, it really is the most natural thing to stop at the curly R valued universal helicity extension. Okay, now this is the refined version of our main result for dog. And then maybe in the last couple of minutes I want to say a little bit about how one starts proving this. And the easier part of the proof is well, so here is how I want to construct our extended helicity that inputs a C0 Hamiltonian structure, capital omega, and outputs helicity. And it's based on this claim here. So I claim that if we start with any C0 Hamiltonian structure, then, well, this might not be homeomorphic to any smooth Hamiltonian structure. And this might just not happen. There are examples of such Hamiltonian structures that are not smoothable. But I claim that one can always localize the obstruction to smoothing inside some C0 plug. So I claim one can find a smooth Hamiltonian structure, little omega, and some C0 plugs, such that this structure here, obtained by putting the C0 plug into the smooth structure, is homeomorphic to the original structure, capital omega. And once one has this claim, one is essentially forced to define the helicity in this way, simply by the properties listed in the theorem. So if our capital omega was homeomorphic to this guy here, then we have to define its helicity to be the sum of the smooth helicity. It's a real number, and we take the image in the curly R, plus this extended Calabi invariant of the time one map of the isotopy in the plug. Right, so there's no choice. Now, of course, then the really subtle part of the whole story is to show that that would be independent of choices. Right, but just to by definition, we don't know that we can find such a little omega in a plug, and then we have to divide it in this way. Now, why should one believe the claim? Here is the idea. So the important observation is that if one has some C0 foliation, and I sketched some picture of C0 foliation here, then locally it's homeomorphic to the standard piece. So locally it's always smoothable. And the obstruction to smoothing a structure foliation globally really lies in the presence of recurrent leaves. Right, so you can smooth locally and then smooth on a bigger and bigger set. And they really only run into troubles if there's a leaf that is recurrent. But yeah, so now our trick is to, first of all, we can just cut some holes into our manifold. So we throw away a bunch of charts. And let's just choose a bunch of transverse little disks. And one chooses sufficiently many of those such that there is no more recurrence in the complement. So one really cuts every single leaf into small compact pieces. That's the first step. Then the second step would be to show that one can smooth the structure in the complement of these blue flow boxes. Because there was no more recurrence in the complement, one can show that the restriction of the structure to the complement is going to be homeomorphic to some smooth Hamiltonian structure in the complement. That's step two. And then so the trouble now, of course, is that if one has this homeomorphism defined in the complement of the flow boxes, it might not extend to a global homeomorphism. So there's some illustration of that, right? So there's some homeomorphism defined in the complement of flow boxes. So in both the left and the right, it's a local picture where the foliation just consists of vertical lines. And then, so that the color is supposed to indicate where which leaf goes. So this orange leaf here would go to the orange leaf here. The red leaf up here go to the red leaf up here. And then, yeah, in this picture, it's kind of very clear that one just cannot extend the homeomorphism that's defined in the complement of the flow boxes over the flow box, simply because, well, leaf has got to leaf, and on the left side, the red and the orange are the same leaf, right? There's a straight leaf going through here. And on the right side, red and orange don't line up. So this G then was functionally extending the G. But the point now is that right, we didn't want to smooth globally our structure. We wanted to smooth it up to a plug insertion. So if in our flow box now one puts in an appropriate C0 plug that reroutes the leaves, then after this operation one can extend this homeomorphism, and this is what proves the claim. Right, so this was this claim here that any C0 Hamiltonian structure is homeomorphic to a smooth one with a C0 plug inserted, and this then forces what the helicity extension has to be. Right, now as I mentioned, then the real difficulty is to show that there was an independence of choices, right? I can write the same Hamiltonian structure, maybe in many different ways, as a smooth one with a plug inserted, and have to figure out why it was that the eccentricities should agree. And this actually, just the invariance is a special case of this. So if we just look at smooth structures with no plugs, right, this invariance statement would be a special case of this key difficulty here. Right, but yeah, so I think I'm reaching the end of my hour. So maybe I would just stop my talk here.
Okay.
Thank you very much.
Thanks a lot, Oliver. That's very good. Any questions?
Oliver, everything you have not explained is constructive by hand. Invariance and what do you use more hammers or is everything by hand or what?
So there's somehow two parts to the story. There's the part on the foliations, and this in some sense is it's like very explicit. So really it ties in very well with the works of Princeton on foliations, old work from the 70s. And well, our kind of arguments they kind of continue this this kind of line of argument. So yeah, this is very constructive. But then this alone is not really so. This is then not really enough to get anything out of it. One really has to combine it with these results from on error preserving homeomorphism groups that do use blur theory. So somehow, yeah, this is really the key fact that shows up repeatedly here is this whole statement of the injectivity of this map. So what it's saying is, if you take a diffeomorphism, a Hamiltonian diffeomorphism, and you assume you can write it as a product of commutators of homeomorphisms, then it already was possible to write the diffeomorphism as a product of commutators of diffeomorphisms. This statement, I'm not aware of any. There's one proof I'm aware of, and it really passes through these spectral invariants and blur theory. Yeah, so the other part on foliations is more constructive by hand, but then really one has to combine these two pieces for our story.
But you just algebraically use what you have from the the spectral invariance. You don't have to develop further there.
Yes, one does not. So yeah, we don't know of a way of defining spectral invariance for the volume preserving flow, because yeah, it could just not be of contact type, so it's to be able to do there. Yeah, so the Fur theory enters algebraically through these connections between foliations and the algebraic structure of transformation groups. That's right.
Okay, and since I'm already on, assume you have finitely many zeros of the flow. Can
Yes.
you kind of open them to and approximate, or is it hopeless? With
Yeah,
your
well,
setting?
so no, it's not hopeless. So we were at some point working out the case of generic zeros. When it's a smooth vector field with a non-degenerate isolated zero, then I think one can take care of these. Yeah, there would be some approximation procedure. If one goes to full generality and has some arbitrary wild zero set of a vector field, we don't quite know yet, and maybe it's not even quite clear which way to conjecture. So we talked to some people, Hessen, for example. It's a priori conceivable things work out differently. It's not quite clear, but yeah, so some certain classes of singularities one can deal with.
Thank you.
The question. May I also ask a question?
Yes.
So when you at the very beginning of the presentation, you were giving Arnold's definition of the linking number of
Right.
two flow lines. Yes, I just wanted to get back to the way you were explaining that you connect the endpoints of each of the flow lines.
Right.
Then you said that we use geodesics. Can you clarify this a bit to me, like geodesics with respect to which metric and how do you define them actually?
Right. So I mean there are some subtleties hidden in there actually, and this is part of what Vogel later clarified more rigorously. Yeah, I mean, so the overall idea is that hopefully these short segments in the smooth world hopefully should not matter too much. That we hope. If as the flow lines flowing for very, very long times, then maybe these little segments here maybe don't affect the linking number too much. Yeah, so I think one way of doing it, and maybe we have to look it up in Vogel's work is, yeah, we just pick some auxiliary metric, an arbitrary smooth metric. And then, okay, then if you have 2 points, there exists, well, there could be, of course, in general, it could be more than one choices of shortest connecting arcs. If there's more than one, one has to just make a choice. But then the idea is that maybe there's not. So, I mean, this whole thing only has to be defined for almost every pair of points. So somehow the idea is that the set of pairs of points where there was an ambiguity actually was a zero set in the end. Right. But yeah, so there's some subtleties. And that the challenge is to argue that in the end it did not depend on the choice of a reasonable short path.
Okay, I see. Thank you very much.
Okay, so if there is no more question, thank you, Oliver, again.